Hi, today we will present our project on applying reinforcement learning to optimize supply chain dynamics in the beer game. Let's get started. In this project, we explore how reinforcement learning can be applied to the beer game. The objective is to minimize costs and mitigate the bullwhip effect, which arise from demand fluctuations and lead time uncertainty. Key highlights include introducing traditional and RL-based policies, analyzing their performance, and exploring mixed policy setup for future improvements. Here is an outline of today's presentation, starting with an overview of the beer game, followed by methodologies, simulation setup, results, and future direction. The beer game is a classic supply chain simulation game, demonstrating the challenges of managing orders, inventory, and demand across a multi-echelon supply chain. Each agent, retailer, wholesaler, distributor, and manufacturer aims to minimize the inventory holding and backorder costs while adapting to fluctuating demand and lead time uncertainty. A key takeaway is a bullwhip effect, where small customer demand changes amplify variability and cost upstream. Beer game consists of four rows, each managing inventory and orders. Let me break this setup into key components. Inventory levels represent the stock available at each agent. Back orders are unfulfilled customer demands due to insufficient stock. Back orders accumulated until they can be fulfilled. Delays occur due to the predefined shipment and order lead times, which introduce lag between placing and receiving orders. Additionally, there are two dynamic variables. Ongoing orders represented by the blue arrows. These are orders placed but not yet shipped. Incoming shipment, represented by the green arrows. These are stock currently in transit to the next stage. The diagram illustrates how demand flows from customers to the retailer and upstream to the wholesaler, distributor, and manufacturer, finally reaching the factory, which assume unlimited production capacity. The beer game operates on a week-by-week cycle with five key steps. First, inventory is adapting as incoming shipments are added to the current stock. Then, demands are processed. Retailer fulfill customer demand, and upstream agents fulfill orders based on what they receive. Next, stock is adjusted to address back orders and new demands. If demands cannot be met, it is added to the back orders for the next cycle. Following that, agent predicts future demand and places new orders to maintain sufficient inventory. This is where the action and decision making taking place. Finally, rewards are calculated, which reflects costs incurred from holding inventory and managing back orders. This slide shows an example of an arbitrary week in the beer game. The blue circle represents orders, while the green circle indicates shipments. In the first row, we see a date at the start of the week. In the second row, shipments have been received. For example, the wholesaler adds 10 units to his stock after receiving a shipment. In the third row, orders are processed, stock is adjusted, and shipments are sent. Taking the wholesaler as an example, it received an order for 30 units but only have 10 units in stock, so it ships out the available 10 units, and the remaining 20 units are added to its backorder counts, increasing from 120 to 140. In the final row, each agent makes a decision to place new orders, showing the blue circles. There have been several approaches in the literature to address supply chain challenges. Early work proposed the use of base stock policy to manage inventory. Later research introduced reinforcement learning mechanism, combining agent-based modeling with Q-learning. Most recent advancements apply deep reinforcement learning techniques, such as shape-reward deep Q network, to decentralized supply chains. This method enhances decision-making by aligning individual actions with overall cost objective. Our simulation have a 100 total weeks with a delay of 2 weeks for both order and shipments. We have an initial stock of 20, holding cost of 1, and backorder cost of 2. Our customer demand is a bell-shaped curve ranging from 10 to 30. The state space for each agent includes 6 values: inventory level, back orders, 2 incoming shipments, and 2 outgoing orders. The action space allows agents to place orders ranging from 0 to 200 units, offering a total of 201 discrete actions. We model this problem as a decentralized multi-agent POM-DP, where each agent makes decisions based on partial observation of the supply chain state. The challenge lies in limited visibility and coordination, and our goal is to optimize overall supply chain performance through effective local decision. We implemented 4 different methods to address supply chain optimization. First, the base stock policy provides a straightforward approach to maintaining inventory at a target level. Next, the autoregressive policy leverages recent demand history to forecast and adjust orders using linear regression, offering adaptability by relying heavily on historical data. For more advanced solutions, we choose reinforcement learning techniques like the DQN and actor-critic approach. DQN employ neural network to approximate Q values, balancing exploration and exploitation through techniques like the epsilon gradient policy. This approach was chosen because it is particularly effective for environments with discrete action space and provides a robust way to learn optimal ordering policy under uncertainty. The actor-critic methods combine the strengths of the policy optimization and value estimation. The actor learns optimal action while the critic evaluates them, ensuring the model improves through feedback. This neural network approach allows for more stable learning and was selected because it's performed well in continuous state and action space, which align with the complexity of our supply chain simulation. By combining this traditional and advanced method, we aim to evaluate the trade-offs between simplicity, adaptability, and decision-making efficiency. The base stock policy is designed to maintain inventory at or above a predefined target. The order calculation accounts for the current inventory, open orders, and back orders. The purpose of this policy is to ensure that any gaps between the base stock level and effective inventory position are addressed properly, maintaining consistent stock level. In the auto-regression policy, we use a future matrix and a target vector to predict future demands. The future matrix, denoted as X, consists of sliding windows of past demand values. The target vector, denoted as Y, containing the demand value that follows each corresponding row in the feature matrix. The feature matrix and the target vector are used to train a linear regression model, which predicts future demands based on past trend.
The first RL method we are going to introduce is actor critic. This method integrates policy optimization and value estimation, where actor network predicts a probability distribution, and the critic network evaluates the quality of the states by estimating its value. For our beer game setting, actor model selects order quantities based on the current states, which includes inventory levels, back orders, shipments, and demand history. Critic model evaluates the state action pairs by estimating its state's value using rewards provided by the environment, which penalize excess inventory and back orders. To be more detailed, we use sharing layers to improve learning efficiency by enabling the model to develop a unified representation of the supply chain's dynamics. Another RL approach we leveraged is DQN. We tried 3Q network, which is simple network, 2-layer convolutional network, and 3-layer convolutional network. Due to limited time and computational resources, we only tried a simple network, and we think this one is actually sufficient for the problem setting. Here are the results for our 4 approaches. The most important metric is the total cost or reward over 100 weeks. To put it simply, we hope the absolute value of the reward or cost should be low. By comparing these 4 charts, we can observe that the simple policy performed the worst, with the highest total cost. The AR policy performed slightly better. Both RL methods significantly overperform, converging to a much lower value. But if we wanted to improve the entire supply chain wisely, we should know which agent is the bottleneck in the system. So in order to target each agent's performance, here are their accumulated costs for each method. We can tell that distributor makes up a big part of the total cost in non-RL methods, and retailer makes up the biggest part of the total cost in both 2 RL methods. In the supply chain system, people usually observe a situation called bullwhip effect. So what is it? It basically means small variation in customer demand at the retail level causes progressively large fluctuations in orders and inventory levels as they move up the supply chain. Over the past few years, people tried different methods to avoid or eliminate this impact using different approaches. So by comparing the inventory among different methods, we can tell that RL-based method can eliminate it pretty well, specifically for simple and AR policy. The inventory levels show large fluctuations, especially for upstream agents. But for AC method, it shows a significant reduction in inventory fluctuations across all agents. Inventory levels remain stable and closely follow the actual demand, even for upstream agents like manufacturer. In this project, we adjust the supply chain ordering management of the beer game by integrating agent-based modeling and RL techniques. We first used simple manually designed policy, and later modeled it as a RL problem and solved it using different methods, including AC and DQN, discussed their pros and cons, and analyzed bullwhip effect. Some conclusions or takeaways is that both simple and AR policy are highly vulnerable and impacted highly by bullwhip effect. Both RL methods shows the robustness due to state-dependent decision-making, but still challenged by extreme variability in initial stages. To improve the performance of this system, notice that the bottleneck might be the distributor. We tried a mixed way which combines AR policy, simple policy, and also DQN for different agents. To be more detailed, retailer uses AR policy, wholesaler and manufacturer use simple policy, and the distributor uses DQN. We found that this mixed policy approach actually overperforms all of others, which gives us a hint that maybe our next step could be trying different mixed methods and see which one performs better. Also, we can try to enhance the Q network architecture. Although we write code for different network, we haven't dived deeply into comparing their results. Another aspect worth trying is to explore other RL methods such as soft AC for improved policy robustness and adaptability. Thank you so much.